Hi everyone, this is my Lab 3 report. This is a quick overview of what I'll be talking about today. And first we'll move into the introduction, where we first have the purpose of the lab is to observe the relationship between distance and axis position on the magnetic field of a bar magnet and dipole moment. And some initial assumptions is that as the magnetometer moves closer to the magnet, the x component of the field increases, whereas if it's far away from the magnet, we'll see a near zero magnetic field in the x direction. So some of the fundamental physics principles utilized is the Biot-Savart law, which shows the relationship between the distance from the observation location to the magnetic dipole moment, as shown to the right. And we also see the distance dependence of magnetic field equation, where the magnitude of the field depends on the distance to the observation location, n, and a constant k. So a quick overview of results is that we have the magnitude of the magnetic dipole moment, the value of n, value of k, and then the experimental and computationally calculated magnetic fields at a 45-degree axis. And we can see that there is some significant difference between those. And so moving into the experiment, we first have the methodology, where first we'll determine the direction of magnetic north with the magnetometer app. And then we'll actually put a ruler perpendicular to the phone so that the phone represents north and south while the ruler represents east and west. Then we'll actually locate the sensor of the magnetometer in the phone. And next we'll measure distances from the bar magnet to the sensor in my phone for different x component magnitudes of magnetic fields and for on-axis, perpendicular axis, and 45-degree axis. And next, we'll plot all of the data collected to determine the value of n, k, and mu from the distance dependence equation. And then we'll compare experimental with computational results. So initial conditions, just the system is the bar magnet and surroundings is everything else. And we'll see that we compare different distances to different components of the magnetic field. So moving into the experimental calculations, I have the magnetic field magnitudes correlated with the distance that we measured them at, which is graphed on the figure to the right. And this will actually help us in future calculations where we're actually calculating n and k and mu. So n is actually just the slope of the graph, which you can see is 2.9296, which is negative. And we have the value of k, which is 5.677 e to the negative 7. And we also have the value of mu to be 2.83897. And we also have the axis at 45-degree angle magnetic field as shown below in the Excel sheet. So moving into the computational model, we first need to model the physical constants. Then we'll actually need to create the magnet at the origin and then derive the magnitude of the magnetic moment, which we already did as shown. So then we'll need to create a function for the magnetic field, which is shown here. Then we'll need to visualize the magnetic field on axis and perpendicular to the axis with a scale value, distances, as well as the specific observation locations. Then we'll actually draw the arrows that represent the magnetic fields on axis as well as perpendicular to axis, as shown. Then we'll actually do the 45-degree off-axis magnetic field calculation, as well as draw an arrow there to represent that value. So as you can see in the code output, we have the visual representation to the left, as well as the value of k, the value of mu on the right, as well as the different on-axis and perpendicular to axis magnetic fields, and the 45-degree angle magnetic field. So moving into the discussion and conclusion, we see that the experimental and computational calculations are quite different, and we could see that it might be attributed to human eye and precision may not be very accurate, or some rounding, measuring, and approximation errors on my end. And some other possible sources of error is inaccuracy in significant figures. Other active electrical equipment could have interfered with calculations, and I could have been more precise when handling my phone in the app. So moving into the first what if question about orienting our magnetic north, we need to see that the readings would have been drastically different if we did not account for the Earth's magnetic north, because the experimental results would then have changed greatly since it would have interfered. So moving into the second question, we see that the direction of the magnetic field would still be the same even with this change, but the magnitude of the magnetic field would approximately double because the two magnets end to end would essentially act as a single large magnet. Thank you.